It was a very interesting, panel discussion. Excellent points made by our panel members. With that, I like to introduce our next speaker from Xilinx. Xilinx is the leading FPGA company in the world, and they are investing quite heavily in artificial intelligence, developing the platforms for AI applications. And I'd like to invite Dr. Shan from Xilinx. He is a senior director focusing on AI engineering at Xilinx. Shan achieved his bachelor and PhD degree from EE department at Tsinghua University in 2008 and 2014 separately. He attended Imperial College in London. He was awarded with IBM PhD fellowship. Within this is like 80 PhDs among the world forever. Awarded to by the IBM PhD fellowship. He joined Baidu Research as senior engineer in 2014, then joined Horizon Robotics as FPGA team leader in 2015. As co-founder, he joined DP Technology as CTO and led an experienced engineering team with more than 100 people, focusing on high efficiency AI processor design, targeting mostly autonomous driving is acquired by Xilinx in 2018. Dr. has published more than 30 academic papers, including CVPR, ICCB, AAAI, and FPGA. Welcome to the summit, Dr. Shan. I request you to address the delegates now. Thank you so much.
Thank you for introducing. So is my signal stable? I'm not sure.
It is stable. We could hear you.
Thank you. Okay, I'm very glad here to introduce the AI trend and the solution. And like the introduction, I'm currently the AI Senior Director in Xilinx, but previously I'm the CTO of DeFi. DeFi is a startup company in China. We work on building the specific AI processors on targeting for FPGA and also ASIC. So after 2 years running, we are acquired by Xilinx. So I and my team joined Xilinx after that. We have about 120 people in China, Beijing, working on the AI solutions on Xilinx FPGA after the acquisition. So I'm very glad here. I just heard part of the panel discussions, very exciting. And I totally agree that there is a trend that recently we don't tell the exact difference between the edge and the cloud. They are unified actually. And for edge side, we have more scenario, for example, the autonomous driving, the health, the Internet of Things. A lot of scenarios happens there, so we need to capture the data by a lot of sensors. But after that, we still need to use the cloud for more complex computing. In there, a lot of complicated tasks happens, like the vision processing, voice processing, or the natural language processing. Take an example, if we do the smart city, we need to capture the people and got the high resolution of his face and the body, and then transfer back the high resolution part of that image to the cloud. But for other background, we don't need to do that. So the edge side, we also need AI to do detection, segmentation, but we need the cloud to do more complex, like the recognition, and also to compare that with database. Also, similar things happen for the autonomous driving. We also need the cloud to help the cars to be more intelligent with a lot of online learning online learning data and models. Okay, so the second trend, I want to go deeper into the vision, into the speech and also the NLP to see what happens about the algorithm architecture there. So for vision perception, we found that recent years, mostly the recent 8 or 9 years, the networks starting from shallow to deep. And also it's starting from the plane to some skip connections, more complex architectures like from BGG to the DenseNet. And also we have complex operators like the spatial attention and the deformable convolutions. And also some low efficiency models. People firstly found that the accuracy is very high, but later they found the computing is too slow. So we need more high efficient models like the ShuffleNet, MobileNet, and EfficientNet. They are more friendly for the platform deployment. So our company, Xilinx, we focus more on this kind of more efficient models. And we also found the trend that the handcraft CNN models that become past. And nowadays we need to use the NAS to automatically to search of the model topology. And also we need to combine with the platform's features, like for IPGA for our processor DPU, we need to combine the architecture features and search the best model for that. And also we found that the transformer not only becomes efficient for the NLP or the and it's also very useful for vision perception. And so we could find from the table in the bottom, from about 6 years ago, even we use similar amount of computation times, computation ops, the flops, similar flops. Our model's accuracy is from the 70% to 75% for the lightweight models. And for the heavy models, we even got higher improvement. Today with the transformer or EfficientNet, we got 84%, comparing with the 77% several years ago. So the same models are keep evolving. And we also found that the single image processing is there from a single sensor. And we also got the multi-sensor fusion requirement. And that could help a lot for the autonomous driving, like the combined camera with LiDAR or 4D radar. And even for industry, for robotics, we got the combined image and the TOF to get more information from the physical world. So for this kind of multi-sensor fusion work, we got some special OPs like the merge and convert operations. Like the figure show that no matter the early fusion or late fusion, and even we got the deep fusion, that we need a lot of computing besides the two sensors processing pipeline. So that will heavily affect the computing architecture and make the latency be very challenging for us. And also the software, when you got the real-time processing limitations, it's hard for our software to be written. So besides the vision part for speech, the models also improved a lot recent years. About 10 years ago, the Microsoft scientists and others, they starting to use the DNN to instead of the Gaussian mixture models for the speech recognition. And then about 2 or 3 years later, we got the end-to-end deep learning models, which combine the CNN with RNN, that the DeepSeek-2 models, for example, to do the IESA. And then we got the attention models, which improve the accuracy by a large step. And then we got the transducer, recently the RNT models, and also the conformer models, which combine the convolution and the transformer. So for the speech part, the models, they are from hybrid to end-to-end. and also from simple CNN or RN to attention models. So the accuracy also improved a lot. We could see the ASR example. And also for the NLP, I have heard a lot of discussion for the GPT-3 models, but it's too large. No matter for the model size or for the training time, it will be hard to be accepted. But the trend is also similar. We're starting from a long short-term memory, and then we got the transformer. And transformer also beat other models in the NLP task. And also we have some lightweight models. For example, the bird-based and also the tiny bird, mobile bird. So that is more friendly for the embedded device. So we got all this algorithm trend. We found that the algorithms keep evolving. The scientists, they no longer stopped their development. And on the other side, these very good models, one side gave the high accuracy, on the other side gave more challenge to the computing platform. Like our company, Xilinx, we put a lot of effort in AI computing. So we have designed several versions of our AI processors. So when we do that, we could see that for the AlexNet, starting from AlexNet, very simple, the plain network, and to the GuLaNet, we got some forward data from the layers and the layers pass and pass. And we also have the DenseNet, which has the depth-wise convolution instead of the point-wise. And also the data may coming from a lot of layers, and the data output data from single layers will transfer forward to many layers ahead. So this kind of architecture evolving will cause problem for the silicon. When we think about the ASIC, when you prepare to tape out an ASIC, you design the RTL and do front end and back end, a lot of simulation, and then do the tape out in TSMC. But at that time point, when you got your samples, almost 1 year and a half or 2 years has passed since you have designed your architecture. So if you imagine, if you design your architecture targeting for AlexNet or that time point networks, then when you have DenseNet, either you will get a very bad efficiency or you cannot run that on your architecture. So we need to find a way to keep up with the rate of the AI innovation from the silicon side. So we need a DSA. So what is a DSA? DSA is a domain-specific architecture. That means we're targeting for a vertical domain, and we design architecture targeting for that domain. And we also could be adaptive to that domain's change. That means from the AlexNet, we could design architecture like this. And when you have the GuLaNet, we could have the architecture like that. And also for the DenseNet, we also have the architecture fit for that. So if you are using ASIC, you will need 3 generations. If you are using GPU, I believe you could use early version of GPU to run that. But the problem is that when you run new models, you'll get very low efficiency on that. So the solution is we could utilize IPGA, utilize Xilinx platform to for this kind of adaptive features. We could program the hardware, and also nowadays we have the AI engines, that is a software programmable DSP array that should help you to tangle for this AI innovation. So the adaptive device will allow the DSA to be updated without the new silicon hardware tape-out. And what is inside the DSA? I said that it is very flexible and could fit for a certain domain, and we got high efficiency. But how we did that? So the first thing is about the customer data path. Even for the convolution, we got several types of that, the point-wise, the depth-wise. And if you design one kernel for that, then the efficiency will be variance across different type of convolution. So you could design the different type of IP using the inside the DSA. You could design a different customer data path. And the second part is about the precision. When we do training, we always hope we could have the floating point data format, even the double. But for the inference, sometimes we found that the fixed point could work. And even when we limited the bitwise to 16-bit or 8-bit or even lower, it also could give us the similar precision, similar accuracy. So with this experiments observation, so that means we could change the precision from the floating point to the fixed point. So in our design, we always use the 8-bit and also 4-bit or even 2-bit for our AI processor architecture design. So that will reduce the resource occupation a lot and help you to initialize many more parallelism processing engines, which could help you to improve your throughput and help with the latency. The third one is the memory hierarchy. So for CNN, firstly, we think that this is a computation bound task. But after several years, we found it is also the memory bound problem. And for the LRP or for the speech recognition, it is naturally the memory bound problem. So we have the memory hierarchy. You could load the weights and the data from the off-chip memory, but that will be very slow due to the memory bandwidth. And you could also initial the buffers in on-chip, but that you will have limited size. So how to organize your data path, how to distribute the memory to fully utilize of the on-chip memory to reduce the off-chip memory access is a very key issues for your AI processors efficiency. So for our the Xilinx platform, we have relatively large on-chip memory, and we do a lot of work to optimize for that. For example, we will do the batch processing and share the weights and store the weights data in on-chip memory. And for the intermediate data between layers, we could also store part of that in on-chip memory to avoid the memory load and store to the off-chip memory. That helps a lot for the efficiency, for the computing efficiency. So I have talked a lot about how we use the DSA, domain-specific architecture, based on Xilinx platform to accelerate the AI computing. But when we think about a real system, the AI is only part of that. Although it's a key part of that, but it is still a part of that. We need some pre-processing like OpenCV, and maybe we got some post-processing like the planning and some decision-making work. So what we need to do is not only to accelerate the AI part, we need to accelerate the whole flow. For example, for the autonomous driving, you need to do that all the things in real time. You cannot only do AI in real time. So how to deal with other part? If you are using some ASIC, some AI processors, which is ASIC-like, you could only accelerate the AI part. But for others, you need to run that on some very relatively slow ARM cores. So, but in our platform, our DSA could also support the non-AI part. We have the OpenCV library, which is accelerated on IPGA. We have other interface, which is also hardware embedded, and also the accelerated version. We have a lot of things which are accelerated. So you could easily, starting from our library, starting from our reference solution, to build up your total solution. So I will introduce the Xilinx proposal. So the Xilinx has a branding called YTCI. Our YTCI is a full stack of the software and the DSA IPs. targeting for no matter which generation of IPJ, starting from 28 nanometer to the 7 nanometer, we could support them all, and using the unified flow. In this flow, we're starting from the frameworks, TensorFlow, Caffe, PyTorch. We all have the support for that. And we even have a model zoo. In there are almost 100 models across the classification, detection, segmentation tasks, and also targeting for the ADAS and smart city and healthcare vertical domain applications. So starting from that, you will find the models that is running smoothly on our platform. And you could, starting from that, to change the model topology to modify and optimize that from there. And how we run all these models on IPJ. So inside IPJ, we use the logic and to build an DPU. The DPU is an AI processor architecture. We build several flavors of DPU, the CN DPU, RN DPU, and also the BERT DPU. And inside the CN DPU, we have several versions. Some are optimized for the latency, and some are for the throughput. And with these DPUs, we define the instruction size, and we also have the compiler combined with this instruction size. That means you have a model topology, and you're using our compiler, and we will compile the models into the instruction sequence, and then the sequence could be run on our DPU, and the DPU is placed inside the IPJ logic. So starting from the 7 nanometer, we have a device called ACAP. In ACAP, besides the programming logic, we also have an AI engine. For that AI engine, and you got the DSP arrays to accelerate your AI processing, and that could be run about 1 gigahertz. That is much faster than the IPJ programmable logic when talking about the frequency. So our flow could also compile the work to that ACAP platforms. We automatically separate the data paths in the logic and separate the computing intensive convolution layers into the AI engines, all by the same flow. And on top of the compiler, we have the runtime. And inside the runtime, we not only support the deployment of all these DPU IPs from the models, and we could also allow the users to register their own OP. That means if they found some model cannot be supported by the DPU, then mostly it will be run on the ARM core inside our device. But on the other way, if some customer, they already have some IPJ IP in the logic part, they could also register that IP and using our flow to combine the DPU IP and their IP to do the whole application acceleration. And we could also support that. And even they don't have their IP, but they have some special OPs, and we also could help them to register that into our software library, and they could use runtime to run that in the ARM core or the CPU, hosted CPU. So we also provide the compiler and the optimizer, which is the pruning tools for users to use and to help to optimize your models. So some key takeaways of our Vertex AI flow. This is a unified AI platform. No matter the cloud application or edge application, no matter which generation of the Xilinx FPGA chip device, you could all use this unified flow to deploy your models. We have comprehensive models in the model zoo and the related library to help you deploy of all these models within several minutes. And also our hardware IP, the DPU IP, will keep evolving. We have several generations, and we'll keep building the new generations of the different DSA for different algorithms. Like we got the BERT in last year, and we will have something new this year. So we are not only targeting for the AI. The Vertex is a larger concept. inside Vitis is part of that is Vitis AI. Besides Vitis AI, within the Vitis, we also have the OpenCV acceleration and other accelerations that could help you to build an end-to-end solution with the AI plus X. The X module is what you previously have, or you start selecting from our libraries. So this will help for your whole application acceleration. This is quite different with other platform you could choose to use. So I will, at last, I will give you 3 examples how to use the styling solution to optimize your AI task. So the first is the multitask perception for automotive. This is the optimization only mostly from the algorithm level. So in our model zoo, we actually in my team, I have about 30 algorithm researchers who keep doing the state-of-the-art models, and also find the FPGA-friendly models and have customers to utilize that. So when we do the automotive customers, we found they always they need several tasks running together, like the vehicle detection, the pedestrian detection, lane detection, and the segmentation, and drivable area segmentation, and also the depths. Some automotive, the tier 1, they also want to use the camera to do the depth estimation to save the cost. So all these tasks, they are all deep learning models. Why not to combine that into single models? So the multitask models, we spend a lot of effort to do that. So you could find the first generation, we combine the detection and segmentation tasks together. And then we found that the latency is better and the throughput is much better for the multitask. And for the multitask version 2, we also do some models combination work. Besides that, we also use the NAS to search the best architecture, which is friendly for our DPU design. And we combine the 3 tasks together. And for the 3rd generation, we use single model for 5 tasks. And we when we see the tables, you could find that for the when you improve the task numbers, and the time consuming is not linear increase, it will help you to save some time. So this is from the algorithm level optimizations, and you could always find that in our model zoo. And we will cover the we already covered the automotive and the smart city and healthcare, and we will cover the robotics very recently in the summer of this year. And another example is how to do the optimization from the compiler side. So I've taken example of the image resolution. This is from a customer who want to use the low resolution to display at a very high resolution for the more friendly display. And of course, this is very heavy deep learning models, CNN models. So the state of the art is the RCN models, but the model is too heavy. And we found that if we want to run that in real time, we need more than 100 tera operations per second. So the first thing we think about is to prune that, to compress that, to make the model be much smaller with similar accuracy. So we do a lot of work in the pruning part. And second, we found that there is an issue. If we using the larger model, you will have more possibilities to explore the parallelism. But if you shrink the model to a relatively small size, then you don't have that much of parallelism, and you need to do some optimizations in your compiler. So we are using some layer fusions and some risk scheduling, and also some the weights preload to reduce the off-chip memory access to tackle this problem. And we also found that we could, when you deal with the image, you could also partition that into several batch, and we could use the batch parallelism to increase the possibilities of parallelism to fully utilize of the so many computing elements. So when we do several operations, several optimizations, you could find that the frame per second improved, and also the latency are improved a lot. So this is a case to tell you that when you use our flow, you could do the algorithm optimizations, the compression, and you could also do the compiler optimizations. So the third example is about LiDAR. So LiDAR is a very important sensor for the automotive, but also for the industry, for robotics, for a lot of things. LiDAR is important. Xilinx is always the very key vendors for the LiDAR products, because we are very good for the DSP processing to generate the point cloud. That is some traditional algorithm to help you to generate that using DSP method. And recent years, those LiDAR vendors, they want also to use the chips to do the AI part after the point cloud generation. And one naturally thinking is that to utilize single chip solution is always better than the multiple chip solutions. So they want to embed that AI also in that FPGA chip. And our advanced AI flow could help them to do this whole application acceleration. But the key thing is that we need to demonstrate that Xilinx FPGA could also run the LiDAR processing. So this is a case for LiDAR, and but we could do much more than this. This case is the 3D object detection. We are using the point pillars, very popular models. And when you go deeper into the pipeline of the point pillars, you will find there are some pre-processings, and there are some feature net, the point net for feature extraction, and the scatter, and then the RPM network to do the detection. And inside that, there are some backbone, the 2D CNN backbone, and also the detection, the SSD detection framework, and also some post-processing. So all this flow, you could tell that this is not a thing only care about single AI models. There are 2 AI models there, and there are also some other non-AI operations there. So for our solution, we combine with we work with this customer and help them to tune from the algorithm part at first. And when we do some dimension reduction, and when we do some voxel number reduction, it could also satisfy their accuracy requirement. So, but that model becomes lightweight for the platform. And we also do the 2 AI models in single DPU that could utilize that by the time maximizing method. And we also do the model compression for the backbone models to compress that by 7 times to 1/7 size. And also there are some software end-to-end flow optimizations. So at last, we accelerate more the 13 times compared with the non-optimized version. So there is a demo videos could show the real time, close to real time. It's about 20 frames per second for the point cloud, for the point pillar 3D detection. And we also released the model for the 3D segmentation for LiDAR data in the most right bottom figures. And you could see that with the, we do a lot of work for that, besides the model compression, and we also do the multi-thread optimizations using the software flow. And of course, we context that model to run that in our DPU. So that are the examples, and I want to give a summary of my presentation. So the first thing is that AI algorithms are evolving very fast no matter the vision perception or the language processing or the speech recognition, the models, they are all evolving a lot. And even more, the multiple model will make that even complex. And we found a very interesting trend is that the transformer is dominate the language processing and also the speech recognition. And nowadays, even for the vision perception, it will become the state of the art. So the second thing is that this innovation requires the domain-specific architectures to meet for the new networks, latency, performance, and cost. So, and also another observation is that AI application is much more than AI only. It's also need the DSA to accelerate the non-AI part. And our Xilinx solution, our Vertex AI solution, could help you to build your system from a software developer's point of view, and to support a lot of frameworks and make the developer very easy to deploy your models within minutes. And I also give some examples to show how to optimize the AI system from different levels, from algorithm level and from compiler level and from the architecture levels with our Vertex AI flow. So thank you. That's all for my presentation.
Thank you so much, Shan. That's a wonderful presentation from you. It's a great insight. And we have a couple of questions from our audience. The number one, as we all know, the computing power and the memory that's needed for artificial intelligence applications. It's like the needs are growing pretty fast. And how do you see, again, also the latency between the CPUs and the memory is also becoming a bottleneck in some applications. So how do you see Xilinx scaling up their hardware platforms, their FPGA platforms, and what kind of architectures they're investing into?
Okay, so as I mentioned in the presentation, we found that the memory is the one of the key things for the computing power. Mm-hmm. And we have some device that has HBM. So with those HBM device, you will have a very large memory bandwidth. So no matter what kind of AI applications you want to do for the inference, those HBM almost could satisfy your requirements. But HBM also have some issues like the power and also the cost. So we know that if you want to have a chip to have HBM interface, then the chip will be much expensive than which don't have that. So with the chip which don't have with reasonable price, reasonable cost, and power, what we do is that we fully utilize the on-chip memory in our DPU design. And we do a lot of optimizations beside between the layers. The intermediate data, we treat that very seriously, and to avoid frequently load and store to off-chip, if we could, we will store all the data into the on-chip memory. But sometimes you will have some large image, large resolution, and large models. It's hard for you to do that. So you need to make decision which part of the data is mostly used. So to tackle this problem, we also have the pruning technology and the condensation technology. The pruning could help you to shrink the model size. Of course, the data size will be smaller, and that gives you more chance to store more hot data into on-chip memory. And the condensation could also reduce the transfer bandwidth requirement, and also could to help you to store more data into on-chip memory. And we have a white paper released early last year that is talking about the 4-bit solution. And we also have the 4-bit IP. With that, it will ease the challenge of the memory bandwidth also. So we have a lot of techniques to solve that problems. Yeah.
Thanks for those inputs, Dr. Shan. One more quick question. So we had a very interesting panel discussion before your presentation, edge versus cloud computing. And where do you see Xilinx FPGAs playing the role? I mean, more on the edge computing side or on the cloud computing side?
Oh, for Xilinx, we focus on both sides. We know that our CEO Victor Peng said that the data center first several years ago, and we proposed the ACAP platform, which are very powerful platform for the data center side. So we treat these two things at the same level. For the edge side, we think that Xilinx is very good there for the sensors, inside sensor processing, and we could do the front end AI and to scan the useful data and transfer that back to the data center. And in data center side, we have SolidFire to do smart NIC, and we could also do the data, do the AI inside the data exchange in the data center together with SolidFire. And also for our the AI computing capability, our recent ACAP platform could reach to hundreds of tera operations per second. So that is also very powerful solutions in the data center. So I see them at the same level, and I think they will help each other. For some customers, some hyperscale customers, they will have a lot of sensors there, and the data acquisition channels there, and they could also have the data center to process of those data. So imagine they cannot accept to use too many different platforms to do the edge and the cloud. They want to unify that. So that's why we provide the Lattice AI, which is unified for edge and cloud. Yeah.
Thank you so much, Dr. Shan. You know, and once again, we really appreciate you taking the time to join us today morning. It's been a wonderful session, and we look forward to having you on similar sessions in the future with us. Have a nice day. Thank you so much. And with